Gaussian integral?
Yeah.
Do you want to ask that question?
It was just like how it's different, how the complex version is different from the real one, and how to figure out the answer.
Right. So I mean, I don't have all. I probably won't have all the details, off the top of my head. But what we know about the Gaussian integral is that if you integrate from minus infinity to plus infinity of e to the power minus ax squared of d of x, we get square root of pi over a, right?
Yeah.
Now, one thing you have to have here is for the real case, a has to be a positive real number, right?
Mm-hmm.
Otherwise, this doesn't converge.
Yeah.
And you know how to prove this, of course, by going to two dimensions, right? And going to spherical, going to polar coordinates, right? You know that.
Yeah.
Okay. Now, what happens when A is complex? Then of course, what happens? How do we deal with this? And so let me just sketch what happens is that, so in that case, what we're doing is, we think of the integral as a complex integral where x is a complex number, okay? Or you can call it z or whatever you want. And so this integral is then you're taking a complex function, because if say a is complex, then the integrand is a complex function, right? And not only that, it's actually an analytic function because it only depends on x and not x bar, right? So then the integral, you're doing it along this contour. This is what you're doing, right? So do you agree that?
Yeah.
So now the way to do it is to actually so when we use complex contour integrals in complex analysis, we use Cauchy's residue theorem, right?
Mm-hmm.
So here the integrand doesn't really have any poles on the, or so if you, whatever contour you take, the value of the integral will be 0, right? So if I take a closed contour, say C, and I take a x squared dx, so x is a complex number, then because this function is a nice function which doesn't have any poles, this will give you 0, right? Using the Cauchy residue theorem, right?
Mm-hmm.
Cauchy's okay. So is that clear to you?
Yeah.
Yeah. So then what we can do is that we can say, okay, let's take two contours, and one contour just goes all the way to infinity. Well, let's take this to be large, this radius to be large, r, and then the length, and then we can just do what we can do is that we can have like a cheese sort of a wheel, like a. Okay, so I'm gonna. Okay, so this is a segment of a circle, and it goes up to 45 degrees. Okay, so, and then what we do is that we just join this over here. Okay. So this is a closed contour, right?
Yeah.
So this part is a closed contour. And this is, for convenience, we take this to be 45 degrees. And then what we do is we then take, for the other half of the integration along the real line, we Okay, I should have it red. We do the similar thing, but now we do it on the other side of the real line. So sorry. Okay. Right. So this is another contour. Right. Now I'm going to leave this as an exercise. What you can do is that you can, you can then use, this. So you can call this contour C1, and you can call this C2, and you can break up, C here into C1 plus C2, right? So now, what I am going to ask you to do is to, write this for this contour, and you can divide x into a real part of x. Let's call it u. The real part of x is u, and the imaginary part is v. Okay. Then what happens? Then you look at what happens to this integral over at on this contour. So part of the integral, you will realize, involves this real integral. So you can use that result. So what you'll find is that the complex contour integral has the same, has the same formal result, but the real part of A has to be positive. And that has to do with the fact that at some point you have to take r, which is the radius of this thing, r. You have to take r to infinity, okay? When you take the limit of r to infinity, the contribution from this part of the contour and this part of the contour will vanish using some, you can, there are some theorems in complex analysis, or you can just show it, just by, you can just see that, upper half plane, it just exponentially, it just decays, because this will have an imaginary part, and this will have an imaginary part, right? So, so I would like you to try it, and then if you cannot do the contour integral, then I can help you again, okay?
Okay, sir.
Yeah, but did you follow the idea roughly?
Yeah, I got it.
Okay.
I roughly got the idea.
All right. Okay, so any other question?
Not really. I'll have to go to the rest of the lectures to see if I have any.
Okay, so since you're the only one who is here today, what I'll do is that I will go through yesterday's lecture again. So you did lecture 18, right? You had a look at lecture 18.
Yeah, and for 19 I did till the path integral to Schrodinger equation. The only thing I missed was the Schrodinger equation to the path integral one.
Okay, so,
Last 2 lectures.
So do you have any questions for the part where we did derive Schrodinger equation?
Not really.
Okay.
I'm not there.
So let me then go ahead and redo the, from Schrodinger equation to path integral, okay?